Hello. Oh my god. Um, I'm back with the two last proofs that I have to finish. I've been putting it off for a while. So, proof 11 is about elementary two forms. And I'm going to write down the statement. Suppose there is a phi, which is an arbitrary element in L squared of 3. And Um, and all that we know about it is that it is multilinear and alternating. We need to prove that phi is sum of two less than three. Essentially, whoops, a this here is phi of some elemental vector I1 and EI2. Alright, the little arrows in. So the general proof strategy in this case is we've sort of done proofs like these before, I think, where we kind of write everything down as two combinations of vectors and then group terms in. And that's kind of what I'm going to do. So let's assume two vectors. Um, and V1 is something like A, B, and C. V2 is U, V, and W. Mm, then once we do multiply this out by, so if this one was V1, E1, we would get um, AE1. Um, Actually, this in terms of E1 is what we want to do. I'm multiplying things out. Plus BE2 plus CE3. And these are like the element of the bases for this. And the other one is going to be UE1 plus UVE2 plus WE3. Alright, so now we can write this down as phi V1 V2 is equal to phi A V1 plus A plus BE2 plus CE3 BE2, which is equal to A. I think we can start removing terms out of it by linearity. So we get V E1 V2 plus B of E2 V2 plus C this P is also linear in its second input. So if you look at the only the first term here, we can write this down as, we should write that down, E1, V2, we can do E1, UE1 plus VE2 plus WV3. And again, by using linearity, we can get, I mean, I'm doing the same thing, so you get E1, E1 plus I of E1, E2 plus EW of E1, E3. Now in this case, E is also alternating, which is something that we know from before. So we can write down stuff like phi P of E1, E2 equal negative E2, E1, and P of E1, E1 is equal to 0. We're going to do the same thing from before and start regrouping terms. So V1, V2 is equal to AV E1, E2 plus B U I E2 E1 plus AW E1, E3 and CU E3 E1, E3 E1 plus BW E2 E3 plus, oh, why did I make this harder for myself? I can just copy them down. Plus CV E3 E2. All right. Now we can start like grouping terms together. So I'm gonna do these two guys. I mean, I wrote them down in that order. So get something like AV minus BU E1 E2 plus AW minus CU E1 E3 plus BW minus CV E2 E3. Which gives me C of E1 E2. The determinant essentially is what's happening in this situation of A U B V plus, I did the same thing, which is E1 E3 A U C W plus E2, E3, det D, B, C, W. E1, E2, dx, dy. This is actually a result that we saw beforehand. So that's how we can write this down. V2 plus E1, E3 dx, and then we cut it on. E2, E3 dy. All right, which is equal to E1, E2 dx, dy, E1, E2. What all is down? Which gives us, so we've written the two form P as a linear combination of what we found out. It should be as of the basis vectors and the basis two forms. So the general form then would be P is equal to, I'm going to continue this down here, equal to P E1 E2 dx dy plus P E1 E3 dx dz plus E2 E3 dy dz. All right, that sort of concludes proof 11. This was actually one of the better proofs. I'll see you back for proof 12 and the last proof of the class.